Good morning. I'm Alfredo Vaccaro and with Meng Wang, we chaired this section of emerging topics. As you know, each presenter has got 15 minutes to present his paper and the first question of 3 minutes. Then at the end, there is a panel where all the presenters could interact with the audience. The first paper is titled Deep Reinforcement Learning for Long-Term Voltage Stability Control. Please, each speaker should introduce it by himself. Thank you very much.
Okay, good morning, everyone. So my name is Hannes Hagmar. I would also like to introduce my co-authors, Robert Eriksson from Svenska Kraftnät, the Swedish TSO, who's also here at the conference, and also Le Antoine, who's an associate professor at Chalmers University, and also the supervisor of my PhD project. Okay, so deep reinforcement learning. I'm going to start off with a little bit of background and motivation for this problem. So I think most of you are very familiar with the topic of long-term volt stability. It's a stability phenomenon that occurs relatively seldom in power systems, but when they do happen, they come with very high costs to society. So it's typically something that system operators always have to take into account during the operation and planning of their systems. It's driven by the actions of load tap changers or excitation limiters and other system components that have quite slow dynamics, and the study period of interest typically ranges up to a couple of minutes. And I've then tried to illustrate the typical development of the voltage magnitude during a voltage collapse. In this figure, typically you have a large disturbance occurring in the beginning, and then you have load restoration occurring in the system, which eventually triggers our excitation limiters, and then you have quite rapid degradation of the system voltages. So obviously, whenever one of these events happen, a system operator never would like to mitigate instability to avoid a complete voltage collapse. But actually, it turns out that mitigating this and controlling the system to stability can be a quite complex control problem. And the reason for this is then twofold. So the first problem actually lies in detecting whether the system is stable or unstable after you had a disturbance. So assuming if you had a disturbance, it's quite difficult to actually assess whether that disturbance is going to cause the system to develop into an unstable state in the future, or if the system is going to stabilize itself. And there's been a lot of research about voltage instability detection methods in the literature as well. So that's one problem. The second part is to determine what kind of actions should be taken in order to stabilize the system. So assuming that we have determined that the system is unstable, what should we then do to stabilize it? And basically, what kind of actions should we take? System operator, they have a large range of different actions, but also in what extent. So if we do load shedding, how much load do we need to activate to stabilize the system? Obviously, we want to minimize the impact on the end consumers. So this complexity, and remembering that the power system is a very complex and nonlinear system, makes it a little bit problematic to use conventional optimal control methods. I've seen papers using model predictive control, but typically you would have to simplify the control problem quite significantly in order to be able to solve it in this quite limited time frame that is a long-term voltage instability event. Since then, system operators quite often rely on a little bit more simple methods. So, I mean, typically the end backup is to use local protection, such as undervoltage load shedding, but they can also use a little bit more analytical approach. And in this figure, we basically dumbed it down a little bit, but it's a very simplified practice how system operators can come up with different control rules for different kind of situations. So what they can do is that they can run different simulations where different typical scenarios, high load, low load, and larger disturbances occurring in the system, and then they can analyze the efficiency of different control actions. And basically by doing this iteratively, they can then develop lookup tables where different actions are then ranked for different kind of situations and disturbances and load scenarios and so on. There's a lot of things to say about this approach, but there are quite a few drawbacks. Obviously, this analysis will be based on quite a few typical scenarios. And quite typically, the actions that you then have in your lookup table would either be too harsh, or they may not be sufficient enough to stabilize the system. Okay, so therefore, we then propose that we theoretically could use deep reinforcement learning to try to optimize this control approach a little bit further. So very short background into deep reinforcement learning. I know there's been one paper before which has talked a little bit about it. So reinforcement learning is one of the main 3 legs in machine learning. Basically, it's machine learning which is adapted for control purposes. It's based on Markov decision processes, which is a mathematical framework for modeling decision-making problems. And then there's a lot of terminology in reinforcement learning. I'll just go through the most important ones. Typically, you have what is called an agent. Agent is the same thing as a controller in control theory. So the agent takes different actions according to its current policy. Then you have the environment, and then the environment is the same thing as the system that we try to control, so the power system, or the plant in control theory. You have the state. State is the same, which is then a representation or the current knowledge that we have about the system in the current time. And then you have the policy. And the policy is what the agent then uses to take different actions. So the policy typically maps the state to an action. And depending on what kind of reinforcement learning agent algorithm you use, it can either be deterministic or it can be stochastic. And then the learning in the reinforcement learning algorithm takes place by doing what is called the agent-environment interaction. So you have the agent taking different actions, which is then dependent on the policy and the state. These actions then affect the environment or the power system, giving rise to rewards, negative or positive, and new states, because it changes the environment as well. And then you basically do this interaction for some time, you generate some data, and then you train the agent. And basically what you do during training is that you want to reward good actions, make them more probable to happen in the future, and you want to discourage bad actions. And by doing this iteratively, the goal is then to find some sort of optimal control policy that can maximize the future rewards. And the rewards are then defined by the user typically. Yeah, I'm just going to mention why we might need deep reinforcement learning. Most real-life control problems, we typically have very large state spaces. This is also true for the power system. Basically, we get our information from thousands different of measurements. Of course, we can filter them and reduce the states, but still quite large state space. And I also mentioned before that the policy, what it does is that it maps the state to an action. So yeah, we need some sort of method or a function that allows us to form a mapping from basically thousands of measurements to a single set of action. And it has then been proven that neural networks can perform this mapping quite well, and it's quite easy to train as well. And basically, whenever you use neural networks for this purpose, it's called deep reinforcement learning. Okay, I'll head over to methodology. So this is the plan of what we want to do. Before we had the system operator doing manual control actions assessing the system. We want to remove the system operator from the equation, maybe not fully, but we want to automate this process, having a deep reinforcement learning agent, taking actions affecting the power system, receiving rewards, and then we train it, and then hopefully we can develop a more optimal policy at least than we would have otherwise. Okay, so this is how we did it in this paper. We used the modified Nordic 32 test system, the updated version of it, which has a sensitivity to long-term volt stability. We then generate a lot of different disturbance scenarios. So we varied the load in generation, we introduced random disturbances in the system, and then we ran a dynamic simulation for each of these different combinations. And in each of these disturbance scenarios and dynamic simulations, we had a deep reinforcement learning agent taking different actions. So basically, we ran the system for 5 seconds, then we had the deep agent taking actions, then we continued to run it until it either collapsed or until it stabilized. So the agent then assesses states and takes different actions. And the actions it could take for this purpose in this paper was to activate load curtailment. And yeah, I'm just going to mention it, but in this paper we model it as being provided by demand response or energy storage systems at 2 different buses in this system. And then, of course, I'll also talk a little bit about the reward and control goal. Basically, all the actions that we activate do have a cost. So activating load curtailment has a cost to the system, but also if the system crashes, we receive a very large negative reward. So basically the main goal of this training is to always ensure that the agent stabilizes the system, but it should also do so by minimizing the amount of load curtailment that we activate in the system. We could add a lot more different rewards to the system, such as, in this case, we just checked long-term volt stability. Obviously, a lot more details about the implementation, but that's detailed in the paper. So I'll just go to the results, because I think the time is running up. So we trained it on 13,000 dynamic simulations, approximately. What you can see in the bottom figure is the share of crashed and stable cases during the training. So in the beginning of the training, we had a lot of crashed cases, but after approximately 4,000 We trained it on 4,000 dynamic simulations. As you can see, basically all the cases have become stable. Then the deep reinforcement learning agent has learned how to stabilize the system. But actually, the learning continues after this as well. In the upper figure, you can see the episode rewards. You can see that it's still increasing a little bit after 4,000 episodes as well. And here, basically, what it learns is how to minimize the amount of load curtailment that is activated in each case. OK, I'll give one example from one of the test cases that we did. Let me see if this works. OK, so the first case is when we had no control. It's the same thing as I showed you in the beginning, disturbance, and then the system collapses. We also compare this control when we had a load shedding scheme, like one of these undervoltage load shedding. So basically, whenever any system voltages decreases below 0.9 per unit, we disconnected 100 megawatts of load from the system. And then the development of the voltage magnitude looks like this. So we follow the same trajectory in the beginning. Then we dropped below 0.9. We do some load shedding. That was not sufficient. We do the second one. And then eventually, the system stability is being restored. Yeah, so that was the load shedding scheme. And now if we compare it to the deep reinforcement learning control, then it looks like this. So the biggest difference here is that the actions can be initiated more or less just after we've had a disturbance. So basically what the deep reinforcement learning agent can do is that it can assess the post-disturbance state of the system, try to estimate whether that state is going to become a collapse in the future, and then choose to activate load curtailment right away. And as you can see, we get a significantly better post-disturbance voltage profile in this case. Also do a small comparison in the level of load curtailment for this particular case. What you can see in the gray lines are the amount of load shedding we activated. So we were required to activate 200 megawatts of load shedding in load curtailment for that case. But when we used deep reinforcement learning control, it was sufficient to just use 90 megawatts of load curtailment. And the reason for this is then twofold. First, we've tried to optimize how much load curtailment that should be activated in this case to stabilize the system. The second part is also we activated a lot earlier. So the system voltages hasn't degraded. We don't have the same high currents in the system, and therefore we can stabilize it with a little bit less load curtailment. Yeah, I'll just go through these results. We tested this on a lot of different test sets where we changed the way how we generated the data. Basically, we tested two when we had new load and generation scenarios, which were not included in the training set. We introduced a new type of disturbance. Basically, we saw that we had quite good performance on each of the training sets or the test sets, but test set 3, we saw that the performance dropped quite significantly. And this also indicates the importance of actually having a representative training set. Otherwise, your performance will drop. But we still got a better performance than the load shedding. I'll head over to the conclusions or observations. So basically, we saw that the possibility of using deep reinforcement learning can then significantly improve the current control systems that we do have and minimize and do it more effectively. I would say that we have a lot of challenges before one of these controls could ever be applied. Just mentioned a few of them, and other presentations have already talked about this as well. But I mean, generating training data that can basically represent all the states that the system can operate in, that's a challenge. Handling robustness issues of neural networks, we've heard other speakers talking about this as well. That's a big challenge. I think one big challenge is also to convince system operators to use black box methods. I don't think Svenska kraftnät would feel confident to use this right away without testing it and really making sure. And then the final thing, which I think is a big challenge, is that basically we train this method purely on simulated data. We cannot go out and test disturbance that might cause long-term voltage stability and train the deep reinforcement learning agent on that data. So we need to always train it on simulated data. And basically, I mean, it's a model. It has to be behave quite well as close to the real system. Otherwise, the control policy we develop won't be as good. I think that was all I had for this presentation.
Thank you. One question, please. Yep.
Thank you very much. Very nice. In terms of getting away from black box side, did you try post-mortem analysis and see what are those very few degrees of freedom which you can probably identify as important, and then the system operator would use it maybe without reinforcement learning?
Yeah, I can say I have not done that, but yeah, it sounds like a good plan to do it in the future. Yeah.
Please, Kostas Vudescu, you.
Kostas Vurnas, National Technical University of Athens in Greece. I have a comment first on your introduction, if I may, and then a question. Yep. The comment is that the current practice, let's say more or less standard practice, is that at the control center you do what is known as online voltage security assessment. So this means that you simulate contingencies, and you know that if this contingency happens, your system is safe or not, yeah, and then you take decisions. Yeah. But you are more on the subject of monitoring, so there are other voltage instability monitoring schemes which you may compare to yours. Yeah. So the problem is to identify the instability when it happens. Now the question is, have you tested cases that are, let's say, marginally stable, and how your system will perform in this case? Will it shed load? Will it recognize that it is stable and not do anything?
Yeah, it's actually, we've included a couple of those scenarios also in the paper. We saw that it has some problems for those marginal cases, that it might sometimes activate a little bit of load curtailment. I mean, obviously that's a big problem as well. So we tested a little bit in the paper with having some sort of action threshold before we activate any levels. It has to be beyond a certain threshold because we don't want to activate load curtailment unless it's necessary. It's actually quite tricky to train deep reinforcement learning, the outputs of a neural network to, I mean, we have, it's a linear output, basically to train that to be completely zero. That's more or less impossible to make it completely zero. So that's a big problem. And I agree with you with the first part about, I mean, systems are typically operated securely. So when I said disturbance, maybe I meant 2 consecutive disturbances or something that might push it beyond the, yeah. Yeah. Yeah, okay.
Thank you. Thank you again. Okay.
Presenting this one, right?
Yes, he'll be presenting this one.
Alfredo?
Yes.
And the video is over there.
Oh, I'm not a presenter, he's a presenter.
He's presenting? Okay, he will be okay. So I'm just doing this. Just double check if it's working. Yep, perfect. Okay.
So the second paper is data-driven models to anticipate critical voltage events in power systems. The speaker is Professor Alfredo Vaccaro from University of Sarnia.
Oh, thank you for the introduction. This paper deals with I mean, the double rule here. This paper deals with we tried to predict some events in power system based on the analysis of data. The starting point is that power system is characterized by a domain where there are lots of data, and we would like to try to extract information from this data. This particular application relies on the prediction of voltage magnitude events. In particular, as we know, the introduction of renewable power generators in power systems is inducing a large number of side effects. In particular, one of the problems that we got in some section of the Italian networks concerned with the voltage magnitude perturbations. In particular, it's important to predict the evolution of the voltage. If there is an overvoltage or an undervoltage, let's say 1 hour before, in order to allow the system operators to activate some kind of remedial action aimed at mitigating the effects of these overvoltage or undervoltage events. This kind of problem, the voltage magnitude prediction, has not been analyzed in the literature as a problem. And we would like to propose a new scheme that allows the system operators to predict the voltage magnitude. In particular, the conventional approach that we could deploy in solving this problem is easy. We have to predict the power generated by both renewable and conventional power generators. We need to predict the loads. We need to know the grid parameters, the topology of the networks, the control systems settings, and we have to make a load flow analysis. That's the classical, the traditional, the conventional approach that we will follow. Anyway, all these input data could not be available and could be affected by large uncertainty. In particular, this makes this problem difficult to solve of computational intensive, because we have to make several predictions, we have to have a reliable and accurate knowledge of the grid parameters and control settings. Sometimes these data are not available or are available with large uncertainty. So our approach is to treat the voltage magnitude at each bus as time series signals, and to propose agnostic models for voltage magnitude prediction. Agnostic model means a model which doesn't need to know, to have the exact knowledge of the network parameters or other kind of exogenous variables. In particular, we try to implement machine learning methods in the task of predict the short, in 1 hour, typically, the evolution of the voltage magnitude in each bus of the network by only processing the measured voltage at each bus. What are the benefits, the expected benefit of this approach? First of all, we formalize the prediction problem as a categorical classification task. So we have got plenty of methods in the machine learning literature that could be adopted for, because at the end of the day, it's a classification. I would like to know if in 1 hour the voltage overcome a fixed level, let's say 1.05 per unit. So it is a classification model, and there are several models that can be adopted for solving this categorical classification task. The data requirement and uncertainty are reduced because compared to other approach, and it is very easy to solve these classification problems because these methods doesn't require very high computational burden. So the idea is to starting from measured voltage magnitudes that, as I said before, are treated by as signals. We try to build a knowledge base. The knowledge base is allowed to describe the input-output mapping of the prediction of the forecasted problem. Then, once we build this knowledge base, we apply one method of machine learning classification after I'll introduce the methods that we have applied. And the system operators know 1 hour before, 1 hour ahead, if there is a certain probability that the voltage magnitude in the monitored bus is outside a fixed threshold. So it could be this kind of tool. By the way, this kind of tool is going to be implemented in real time in the Italian transmission system, by the Italian transmission system operator. So the idea, very briefly, is to solve a classification problem. We have got a time series. Actually, we are working only on the voltage magnitude in each buses. Obviously, in the near future, we are going to analyze the correlation between the voltage magnitudes at several neighbor buses. So the input to these classification problems can be included also other voltage magnitude in surrounding buses. But in this application, we worked only for the voltage magnitude in each buses as input. The output of the classification problem is 0, 1. 0, no overvoltage is expected. 1, there is an expectation. Obviously, this kind of model, classification model, are based on probabilistic models. In fact, the first model that I have developed was a Markov chain model based on adaptive identification of the state probability based on the of the measurements, of the voltage measurements. But my associates, co-authors, applied other kind of classification methods, which are based on stator vector machine, on fuzzy-based classification, and so on. In this method, the problem is how to identify the threshold that allow us to classify the overvoltage event. We applied several methods several conventional methods of classification coming from machine learning literature, in particular, classification regression tree, random forest, k-nearest neighbor, support vector machine, naive Bayes, linear discriminant analysis, and time Markov chain, which is the one that I worked on. And we applied these methods, classification methods, in the task of predicting if, in 1 hour, there will be an overvoltage. Namely, the voltage magnitude is greater than a fixed threshold, let's say 1.05. To assess the benefit, the accuracy and the reliability of this model, we defined some metrics, because obviously the problem here is the true positive, true negative, false positive, false negative, and so on. So in order to test the effectiveness of this model, we needed to define some kind of proper metrics. We define this one, they are explained in the paper. Namely, as far these metrics are closest to 1, better is the model, in poor words. We applied these methods in the task of predicting the voltage in a real sub-transmission system of the Italian power networks. This section of the transmission systems is characterized by a higher level of wind generators. There are a very, very large number of wind generators in that area. Hence, the voltage in this network, in this section, is very variable. So the transmission system operator would like to predict in 1 hour ahead if some configuration, some system evolve toward an overvoltage. The network is composed by 15 bus. And the first issue, when you apply the machine learning, you have to build the knowledge bases. The knowledge basis is the core of a machine learning algorithm. The knowledge base should be composed by an exhaustive training set. So you need to, obviously, to train something, you have to have a training set which is sometimes should be coherently composed by different states. In particular, if we define an overvoltage as a voltage magnitude greater than 1.05, in the experimental data, which are based on 1 year of observation, we noted that there is a good balance between positive and negative events. So the sequence of the output is composed by 0 and 1 in a good balance. If we rise, for example, the voltage to 1.01, we see that, for example, in bus 6, only 1% of the samples are referred to an overvoltage. So it's difficult to, because you have not enough data to training the system. Obviously, if you have got a large number of data, you can improve the training process. That's why we considered also this aspect. What does it happen if I have got a balanced training set of if I don't have a good balanced training set? Obviously, the performance of the machine learning algorithms will be affected by this event. These are the metrics. These are the results. Each of these figures depict the performance of each classification model, considering all the metrics. How do we need to read this figure? Larger the figure, better the method. As you can see, in the red line is in the blue line are the result for the balanced data set. In the red line are the result for the unbalanced data set. As you can see, for the balanced data set, the performance of all these methods are comparable. So when you have got good data, representative of a reliable number of events, all these methods tend to give you the same results. There is not one method which is better, much better than other. When you consider, in particular, the other kind of, was the result from WAP buses. If you apply this method for all the grid buses, as you can say, the performance, the accuracy of the methods changes. It means that some methods works well for some kind of buses, where probably there are some kind of conditions that are, this method is better, because it tries to describe better some kind of phenomena. And on the other hand, when there is a balanced training set, again, no model is superior in all circumstances. Sometimes it's better, sometimes it's worse. So, situational awareness in complex systems relies not only on the visibility of existing state of the system, but also on the capability to predict events. In this paper, we considered as events the overvoltage, the probability that the systems, the voltage magnitude, is greater than a fixed threshold. To solve this problem, rather than trying to identify, to predict the exact value of the voltage magnitude, we try to predict a binary variable, 0, 1. 1, there is the event over voltage, 0, there isn't the event. To solve this problem, we applied all in our own opinion, all the most powerful tool of classification methods proposed in the machine learning literature. And we tested these methods based on experimental data. On the basis of this experimental data, we can say that the problem is well posed if you have got a balanced data set. And all these methods, the performance of all these methods is comparable to each other, again, if you have got a good knowledge base. Just for, I also reported here the application of this method in real-time operation. As you can see, this is the Markov chain. The Markov chain gives you the bounds of the under and lower voltage compared to the real voltage predicted. This is the real voltage. This is the upper bound. As you can see, the method is reliable in the sense that it allows you to predict with a good degree of accuracy the voltage magnitude in these buses. This is an example of how the system works on experimental data. Thank you very much.
Maria Ilic from MIT. To build correlations from your experiment on one node on the network, there has been a lot of work, early work. Jim Thorpe, I've done some with him on, given the network, you can actually know how far the localized response is, and most of the time it's localized, but then you have these outliers if capacitive network and nature of the network is large and so forth. I think it would be fascinating because I think it's the combinatorial problem. How do you go from one node to real network? I don't know what the state of art is in learning tools for scaling up, but I think we somehow have to combine these qualitative properties of physical propagation in the networks to build these correlations. Otherwise, it's just going to be a lot of numbers. I wonder, what do you think about it?
It is exactly the actual direction of our research. We think that if we consider also, there is a strong correlation, I agree with you. And in my own opinion, when you consider also as input the voltage in near buses, the information is higher, the level of information. I think that the only thing that we must avoid here is the redundancy of information, the curse of dimensionality. If you have got too many data which does not put information into the system, that's a problem. But in my own opinion, the adoption of the correlation is a very great option to improve the performance. Because I agree, the networks, the bus are correlated, the voltage magnitude at each buses. So we are trying to...
Not always in a very intuitive way.
No, it's not trivial, no. Because it's a gnostic model. We don't know exactly what is the structure of the system. That's exactly the point. Okay. Yeah. Thank you, Maria.
Jochen Stiasny from DTU.
Okay.
So I wonder, since it's model agnostic, you don't exactly know the parameters. But then if the parameters change in the system, how would you detect that? Because then the model is not necessarily applicable anymore.
I forgot to say that another very nice feature of machine learning is the adaptation capability. So there is an online process which adapts continuously the classification problem. That's another good, when the system changes, the machine learning algorithm adapt to the changing,
But then you cannot really trust the prediction. Like you can, afterwards you
probably
can
when the system changes, you make a mistake in the prediction. But then you learn the new state of the system. This is the concept of adaptation, which is another keyword that, in my own opinion, is extremely important in this kind of model, to continuously adapt the model on the basis of data. Okay, I think we have enough time for other. Okay, so
there we go. It's paper number 54.
the third paper is titled Quantum Computing for Power Flow Algorithms, Testing on Real Quantum Computers. Thank you.
Good morning. My name is Brynjar Sævarsson, and I will be talking about a very new topic within power systems, that is quantum computing, and I will give an example on how we used real quantum computers to perform a load flow calculation. So during this presentation, I will give a quick motivation of why we are looking into quantum computing, and as many of you in our field of research are not familiar with quantum computing, I will give a quick overview of how it works before going into the actual method and the results. So why are we considering quantum computing? Well, as you all know, with power system transitioning towards more and more renewable energy, we have a lot more variables in our systems. We have more fluctuation, uncertainties, and this puts a lot of strain on the computational complexity. And if we want to ensure that the future systems are stable with thousands of new fluctuating sources, we have millions of new operating scenarios which we need to consider, and to ensure that they are all stable or doing optimization, training machine learning. Yeah, we definitely need some new and more powerful tools, and we see quantum computing as to have the potential to handle this complexity. But what is quantum computing? So it was first theorized in the 1980s with the first 1 and 2 qubit machines appearing in the late 90s. But right now we are actually seeing an explosion in the development of quantum computing with devices being built now with hundreds and soon thousands of qubits. I'll come back to what qubits are. But these computers have been shown to, at least in theory, to solve certain problems exponentially faster than classical computers. For example, searching databases or factorizing large numbers. Now, classical computers, the problems can be split into two, like easy problems and hard problems. Now, with quantum computers, we have this kind of overlap. So quantum computers are good at some of the problems that classical computers are good at, but they're not better at everything. So we still have a bit of areas where classical computers are good and quantum computers are bad. So future applications will most likely be some sort of hybrids where the quantum computers are more specialized tools. There are also some areas where quantum computers can solve problems which classical computers are simply not capable of. But this is still a very open topic. But how does it work? So the fundamental building block of the quantum computer is the quantum bit, or qubit, which, unlike classical bits, can be both 0 and 1 with a certain probability. So and only when we measure this quantum bit will it collapse to either 0 or 1. So for each qubit, we have 2 variables assigned to it, the probability of it being 0 or 1. And if we want to visualize a qubit, we can think of it as a vector to a point on a sphere. So like the one we have here on the right. So here we have a 0, we have a 1, but it can also be somewhere in between, like having a probability of being 0 or 1. So this gives us a lot of potential, because when we start to scale up, we have 2 variables assigned to each qubit. But when we want to describe a combined multi-qubit system, it actually grows exponentially. So with 2 qubits, we have 4 variables. With 3, we have 8. And if we go up to 300, we have more variables than there are atoms in the observable universe. So this gives quantum computing very unique capabilities. And many algorithms have been created which are capable of providing exponential speedups. And one of these, which we are using, is the HHL algorithm, which is for inverting a matrix. And this is a central part in many of our applications, such as PowerFlow. And we can see the best classical methods, they scale pretty much linearly with the system size, while the quantum can scale logarithmically. So for very large systems, we can really see some speed up. So we have used this to try to make a PowerFlow. We based this on the fast decoupled load flow method, since it fit very well with the current hardware capabilities that we have. But since real quantum computers are still quite small, we can only perform a part of our algorithm, that is the matrix inversion itself. So each iteration of our load flow, we send data to the quantum computer and then receive a measurement. And as far as we know, this is the first time in the world that someone successfully performs an AC load flow on a quantum computer. So quantum computers are programmed using quantum circuits, like this one shown over here, where we use these logic gates to perform rotations on the quantum bits, compared to regular bit flips in classical computers. So this circuit describes the HHL algorithm for doing a matrix inversion. It consists of 3 steps. We load our data into the computer, we solve the system, and then we do a measurement. And what we get out of this measurement is since we have 5 qubits, we will receive a 5-bit string, where we are mostly interested in 2 of these bits in this case, since the algorithm needs us to have a 1 on this bit, and then our data is encoded on one of the other bits. Now, just getting a 0 or 1 is not very useful, since we want to solve this matrix here. So we need to run this multiple times to get a probability distribution, which provides us with an estimate. So if we run this circuit 1,000 times, we get this 0 this many times, a 1 this many times, and this represents our variables theta 2 and theta 3. So when we rescale this, we get an estimate, which is pretty close to the classical. But in this case, we were using a noise-free simulated quantum computer. But we also did this using a real quantum computer. But the main difference here is that we now see a lot of noise in our system. So the result we get is not as close to the classical one. But if we do this, do the iteration of the power flow, we can see that using classical and simulated quantum, we get a very similar performance. While we tested this on 4 different quantum computers, just to get a comparison of different devices. And we can see that for all of the real quantum computers, it takes a lot of time to converge because we have this noise. Now, we also wanted to see what happens if we want to scale this up to a larger system. So we went to a 5-bus system. This now required 7 qubits, which is the most that we have access to at this time. And we can see the classical and simulated performance is very similar, while the real computers are now even more noisy. And this brings us to some of the challenges that we have with quantum computing. When we are using this algorithm, when we try to scale it up, the circuit depth actually scales exponentially. And by circuit depth, we mean the number of gates used in the circuit. Now, each of these blocks contains a lot of basic gates, but you can see that for each step, it scales really fast. And when we have noise in the system, for each gate, we add a little bit of noise. So if the number of gates scales exponentially, the noise also scales, which can be a big problem. Another problem with this algorithm is the condition number, or the ratio between the largest and smallest eigenvalue in our admittance matrix. For this method to be faster than the classical, we kind of require the condition number to be pretty stable when we scale up the system. But this is not quite true for power systems, as we tested this on increases on different systems, and we can see that the condition number also grows very fast with system size. And the final point was extracting this information, doing this 1,000 runs for each iteration, and extracting the data. This can be really bad for our performance. But we are expecting that with the upcoming software update of the quantum software, we will get some more looping capabilities and can hopefully solve this problem. Now, with our results, we might say that power flow is maybe not the most interesting use for quantum computing, as classical computers are still quite good at that. But it's a good starting point for identifying the potentials and the challenges that we might run into. But there is still a lot of areas where quantum computing can truly be beneficial when we are doing many repetitive simulations, Monte Carlo simulations. If we want to do optimization on many different scenarios, quantum computing can actually evaluate functions for multiple values at the same time. And there are still a lot of open options here. But as quantum computers are not perfect, the early QC will at least most likely be composed of a mixture of both classical and quantum. Now, to sum up, quantum computing has good potential to solve certain problems really fast. However, it's still very early in the technology development, and it will probably be a few years until we will see practical applications. But this approach that we took, taking a classical method and just trying to run it on a quantum computer, is probably not the optimal approach, and we should more look into what quantum computing is good at, and there's an exciting opportunity here to find new ways to perform power system calculations, and we can even ask, do we need to reinvent the basics of power systems? Right. Thank you.
Thank you. Is some questions, please?
Ms. Shertkov, University of Arizona. Very nice. So it's certainly good to see new methods brought in. And I agree with you that probably more hope will be in the future for statistical problems. Well, hope for resolving those through quantum computing. But my question is, you really didn't experiment with quantum computer, right? There are very few, they're kind of lucrative. And did you really get access to using some quantum computer?
Yes, IBM, they have open access to these very small quantum computers with 5 and now up to 7 qubits, which are open for everyone, so anyone here can play with those.
Thanks. Mm-hmm.
Yeah.
Dominic, sorry? Dominic Ross, University of Wisconsin. So this noise that you showed in the quantum computer, is that a bug or a feature? Can you somehow use that to sample uncertain parameters? Since you're now kind of solving a lot of linear systems basically, could you somehow exploit that to get scenarios, random variables into your OPF?
I couldn't quite hear you.
Okay, sorry, let me try again.
Yeah.
So the noise that you observe in your quantum computer, is that a bug or a feature? Can you use that to get somehow probabilistic variables into your power flow problem?
So the noise is a big problem that we have, and there's still a lot of work just to try to get rid of this noise, because it really limits what we can do. To use the noise, we have not looked into that. We currently see it as a major problem, and but maybe there are opportunities in using that. But yeah, I cannot really say that.
Or just the last one, yeah, because after in the panel we got the chance to discuss. I think there are some. Yeah, please don't worry. Just the last one, yeah.
Hi, Abby from the ANU. So you mentioned this idea of the circuit depth increasing quite a bit, right? And that's because you're adding more qubits. But there's also this idea that, in quantum computations, you can add more qubits, but then you can just concatenate to the larger Hilbert space and just do one computation. So is that something that you've explored at all? Is that something you can use to reduce that circuit depth?
We haven't gotten that far with our experiment, but the goal is really to try to reduce the circuit depth, because right now this HHL algorithm it cannot provide an efficient circuit for any kind of matrix. So if we try to adjust our matrix structure and the algorithm, we might get better results with the quantum circuits. But yeah, it's very important to try to reduce the size, and maybe if we can spread it onto more qubits. But right now we're very limited in the amount of qubits that we have. But it's definitely something we will explore.
Thank you.
Okay, thank you very much again.
Okay, the next paper is a comprehensive framework based on dynamic and steady-state analysis to evaluate power system resiliency to extreme weather conditions. The speaker is Mode Korsen from Arizona State. Thank you.
Good morning, everybody. My name is Mojo Korsen Hedman, and I'm an assistant professor at Arizona State University. So today I want to talk about this work that has been done by my master's student. This is the first research paper that he submitted. So it's, he has still follow-up steps that he wants to do, but we figured that this is an interesting subject also to discuss with the research community. So why resiliency? Reliability is usually can be categorized as keeping the lights on, whether it's a binary value, whether it is on or off. And resiliency can be categorized as the process of keeping the lights on. So if there is a disturbance, can be predicted, can we avoid the damage, can we reduce the damage, and can we fast recover from it, and can we learn from it and then apply it for any future events can happen, like predictive analysis that was presented earlier today. And why it is more important to do resiliency analysis these days? More data is becoming available. So first of all, we have more data so we can evaluate the resiliency of the system. But also, there's more frequent extreme events like weather-related event or cyber attacks. So all in all, grid is changing a lot. And with the new assets that are being added, they're more intelligent, and it enhances the ability of one, evaluating resiliency, and two, enhancing the resiliency itself. So now, that was a general discussion about reliability versus resiliency. Particular to this work, we are trying to also capture the behavior of protective devices and dynamics of the system while we are trying to do resiliency analysis. Why is that important? Because protective devices were involved in most of prior blackouts. At least, multiple reports said that more than 70% of prior blackout involve protective relay operation or misoperation. So if we want to evaluate system behavior after an extreme event, then it is important to capture all the critical components that usually respond to extreme events. That includes control system and protective devices and all dynamics of the system together. So the figure on the right here is conceptual. So it's basically what it is saying is that as the severity of the event that we are analyzing increases, we have to include more and more details within our analysis. I mean, there's a saturation point, of course, but when we are talking about N-1 N-1 situation, steady-state analysis can be considered sufficient. As the number of outages increases, then the dynamic analysis with protective devices become more and more important, right? So what we're trying to do is bridge the gap between the prior resiliency analysis that are mainly based on steady-state analysis to more detailed modeling of critical assets related to that particular severe event that we are trying to evaluate the resiliency of system for it. So what this particular paper is proposing, one is a framework that incorporates transient stability analysis with protective device modeling for resiliency analysis, and then also studied the aggregated evaluation of the steady-state and dynamic analysis together for resiliency evaluation. The other thing is that it also studied the interdependency between infrastructure versus operational resiliency and the importance of looking at both together simultaneously. All right. So this is the prior work that looked at the resiliency evaluation, look at a figure similar to this. The first phase can be considered as a prediction when we are trying to use the historical data to predict whether how is the event progressing, what is the trend of weather, and how it is hitting the power system. And then after that, in the second phase associated to the absorption of the event and adoption to it, and then recovery, and finally the recover operation after that the lesson can be learned from it accordingly. So the one thing that was previously looked into, but briefly, was that there can be multiple steps. It's not as clear-cut and linear as this initial figure that was proposed in initial studies associated to the resiliency evaluation. There are multiple steps. Like, for example, in the restoration phase, there's a part of restoration that is operational dependent and not infrastructure recovery dependent, and the operational, for example, redispatch of generator, topology control strategies, and so on and so forth that can help recovering part of the load, and then the rest of it are dependent to the infrastructural recovery, like rebuilding the transmission line or tower, and all of the other infrastructure damage that might have happened. So in terms of the algorithm approach that is taken for this particular paper, without going to every single box in here, so what every single block in here. So what we are doing is that we are evaluating the system performance for a long period of time, let's say 400 hours, and a part of this duration is involved in an extreme weather event. In particular, this paper studies hurricane, but other events can be similarly evaluated, right? So what it does is that for each severe changes that happen in the system, that is outage of an asset or recovery of assets, transient stability analysis is conducted. Protective devices are also modeled in this transient stability simulation. And also, optimal power flow analysis is conducted. That is to evaluate any steady state related violation that can be observed and result in any other, load loss or generation outage or transmission line outage, right? So all in all, then this data is collected and aggregated in a metric associated to the resiliency evaluation. Disclaimer: this table is the metrics that we use, but we did not develop these metrics. These were presented in prior work. We extended it for probabilistic analysis. I'll talk about that. But the prior work only relied on on a steady state analysis, and this particular work that I have a reference for it is optimal power flow based approaches, right? So the first metric is basically evaluating how fast is the drop of the system performance. The system performance can be the amount of load served, the amount of generation connected, and so on and so forth. So the first metric is saying that how steep is the drop of system performance. The second metric is associated to how long does it take to stay in this most degraded state. The third is associated to how fast we are recovering, recovery time, and finally the area under curve that can be normalized with respect to the 100% performance metric. Another note here, we are using RMS simulation for transient stability analysis. The more detailed analysis like EMT simulation also is important when we include inverter-based resources within this analysis, and I'll talk about that briefly later as well. All right, in terms of the test setup, this is tested on IEEE RTS system. The Siemens PSSC software is used for both AC optimal power flow analysis and transient stability analysis. And these are just a brief what is modeled in terms of the dynamic model. Distance relays are modeled, out of step functions are modeled, and under voltage and under frequency load shedding relays are modeled. These under voltage and under frequency load shedding relays are the ones that are responsible for disconnecting part of the load, which then is integrated into the system performance metric and the figures that I will show you. In terms of the how we develop the outage scenarios is that based on a scenario of wind forecast for the initial study of deterministic analysis, there is a probability of failure for each of the assets. This is different if the asset is robust versus not, versus old, based on the aging of the asset. And then based on this probability value, it is evaluated based on a random number whether the asset is experiencing an outage or not. This is, of course, in a simulation framework that I'm discussing. And based on that, then the rest of the analysis is conducted as I talked about it. A little bit more about the simulation setup. As I mentioned, 400 hours, different hours are considered, and and then there is an extreme event in one area of the RTS system that is between hour 51 to hour 75. And then different structures are evaluated. A little bit more about the setup in the steady state analysis. When the asset is experiencing an outage due to an extreme event due to a hurricane, that asset is not recovered in the rest of the simulation. However, till minimum time to repair after the event is done is actually observed. In the dynamic simulation, similarly, the asset that is experiencing an outage due to the extreme weather condition is not brought back up till the end of the event and the minimum time to repair after that. However, the assets that are disconnected by relay operation, like generator assets, those are recovered like 20 minutes later within from the initial time that it was separated. So just walk you through the results that we got. The two figures on the left are associated to the aggregated analysis. Aggregated analysis is referring to the dynamic plus steady state analysis, and then figures on the right are steady state analysis. As you can see, there are more dips in terms of load and generation system performance. The short period that you can see here is because we generously brought the element that is disconnected by the protective relay back 20 minutes after the initial disconnection, and that's why these are a short drops that you can see. But as you can see, there is like a lot of them, so there are a lot of operations, in particularly in this curve for load, under voltage, under frequency, load shedding, and then if you use only a steady state analysis, it's just this clean cut line, because none of these load sheddings would be observed in that type of metric and analysis as well. All right, a little bit more emphasis on why it is important. Of course, this is an initial study. In this particular hour, there was an out-of-step generation, out-of-step relay operation that then the rest of the system was stable. So instead of, if we did not model these protective relays, these out-of-step relays, the entire system would be categorized as an unstable, and the less amount of load would have been served within the simulation. So that's just to emphasize importance of protection modeling. So these are the metrics that I talked about earlier, the slope of absorption, the recovery, the time interval, and the area, and the comparison between a steady state and aggregated analysis. As you can see, aggregated analysis are showing more severe values for these metrics. For OR is associated to operation resiliency, and IR is associated to infrastructure resiliency in this table. All in all, analyzing the system based on the steady state analysis for an extreme event is probably not the best approach, because what dictates the system behavior in that condition is dynamics of the system and protective relays, and without modeling those, we won't be able to evaluate system performance properly. So that was the initial results. We did a little bit of additional analysis on this. One is that we often hear that, for example, this weather condition is hitting Florida, but then the event really unfolds a different way, right? So the prediction is not accurate. So it is important to, when we are looking at, for example, the resiliency of power system to a particular hurricane, it is important to do a probabilistic analysis, because how really the event unfolds in terms of the weather itself, the direction of the weather is different, and then also how it hits different power system assets might be also a probabilistic nature. So it's important to do probabilistic analysis when we are talking about even a particular extreme event that we want to target for an resiliency analysis. The other thing is that there are different categories, of course, for example, in this particular case, hurricane, as it is listed here based on the National Weather Service. Also then these are different categories that we also studied. Other consideration is that there is there are a lot of interdependency between critical infrastructures like transportation system and power system. And even though if we don't want to do all of the resiliency analysis for these infrastructures simultaneously, it is important to capture critical elements. For example, during an evacuation, after an evacuation notice might be an increase in EV charging for people that want to leave that area, right? So that's another consideration that we considered in this follow-up study as well. The other thing is that for particular case of hurricane, if the wind speed is higher than a cutoff speed of the wind turbine, then we lose that generation as well. So this is just basically the same framework as we had, except that this is a probabilistic analysis for how the severe weather condition is unfolding, and then the probabilistic analysis is conducted based on both dynamic and steady state analysis, and the resiliency metrics are developed. So that's where the probabilistic analysis is conducted. So the figure on the right is showing that the number of asset outages in different scenarios that we analyzed for category 1, category 2, and category 3 hurricane scenarios. And the two figures on the left are showing the area under the curve for different categories and for different of these scenarios. As expected, of course, the more severe weather condition, which is the category 3 here, is showing the less resilient response of the system. Similarly, a comparison of different categories of the event and their aggregated versus the steady-state-based analysis, you can see that the matrices here are showing that with dynamic analysis, system performance are more degraded than what a steady-state analysis can communicate to us. That's just to emphasize that if we rely on a steady-state analysis for evaluation of performance in these extreme conditions, we are really not, doing a adequate job evaluating system response. So to conclude, a comprehensive analysis was conducted that included dynamic analysis and steady-state analysis. Within dynamic analysis, we modeled critical protective relays, and then we evaluated system performance altogether with via probabilistic analysis as well. One special consideration that is left for the future work, the dynamic analysis that we conducted was only RMS simulation. So when there's a high penetration of inverter-based resources, it becomes more important to do RMS and EMT co-simulation, and that's what the student is going to do for his PhD study as well. And then there's a co-analysis of transmission and distribution system because of all of the microgrid formation that can happen and utilization of distributed energy resources to serve the load within the distribution system, which impact the resiliency analysis. That is also left for the future work. Thank you very much, and that's what I had. I would be happy to answer any questions.
Thank you very much. Robin Preece, University of Manchester. It looked on the probabilistic analysis that you'd done, say, about 50 scenarios, 50 samples. Obviously, this is quite an intensive computational process, but I was just wondering if you know how many you think you'd need to actually kind of converge towards some reliable results.
That's a great question. Thank you. And yes, it definitely needs more study for probabilistic analysis. And you're right, it's a computationally intensive analysis, but the scenarios can be also evaluated in parallel framework to improve the simulation, reduce the simulation time. But as I mentioned, this is an initial work. That's why the 50 scenarios also analyzed. Mladen?
Mladen Kezunovic Texene. I just have a few comments, suggestions maybe. This problem is pretty big, and somehow attempting to generalize a big problem may not be practically useful at the end of the day. For example, if you're talking about relays, there is no such a thing as relay has operated and you go back and you reclose. There are a lot of things that are done before any reclosure happens. Correct. And you have breaker lockouts and things like that, the overrides, and so it's not something that realistically happens. So it would be nice to look at the intervals when the relays operate, and they have auto-reclosing sequences and all of that, and see what the outcome of that might be.
Yes. And
then how the recovery may take place after the relays operate. At the other end of this, looking at the weather, one has to separate the weather events that are not destroying anything, just causing events to happen, versus, you're mentioning hurricanes that are basically destroying the infrastructure. It's totally different, time scale. So the bottom line is, my opinion is that, if you look at resilience, you have to be very much aware of the spatial and temporal components of that analysis and try to capture certain elements at the time of that and try to analyze how one can recover from these intervals of time and the space, how far the event spreads. So it's just a suggestion, really.
Thank you very much. You're right, Mladen. As I mentioned, there is like a lot of interdependency between different systems to begin with. So if we really want to do a proper job, we have to actually capture, for example, natural gas pipelines, and then electric vehicles, transportation system, and all together. But also that is definitely there, but we have to start from somewhere to do that type of analysis, and that's kind of where we are trying to do improvement. And the other thing is that you're right in terms of the protective modeling devices and how the reclosing is happening. That's why I use the word generous to reconnecting it. This is an initial work done by master's student for his thesis. So yeah, that's true. For the more detailed analysis, those are other elements that can be included. Thank you. Thank you very much.
So let's move to the last paper. The title is Machine Learning for Electricity Market Clearing. Misha Chertoff, please.
Thanks a lot. Thank you very much. Enjoy. It's my third IREP and actually third time in Banff too. So it's a beautiful combination. Also great to see Windows open finally. I'll start with, reminding some of you, maybe attracting your attention to this remarkable book. How many of you know about this book? Okay, great. Yeah, so enough of people. It's actually, I read it first when it was published as a really bestseller. Didn't really pay much of attention. Now I study it more like research book, research paper. And I'm not alone. In a machine learning community, in particular, Yoshua Bengio, in his 2019 Neural IPS big address, he actually used terminology, even though not citing this book explicitly. And what he meant to juxtapose System 1, which operates automatically. Of course, now taking from psychology into realm of machine learning, against System 2, when we allocate attention, we do effort, we think. And he was actually talking about next generation of deep learning. And so now what I want to suggest, and again, I'm not alone, is that a lot of deep learning use in applications, in particular in power system, is about using it as a System 1. Basically, automatic, remarkable tool, but where we really need to think and focus is on the System 2 aspects, which of course, will always be there, and that's what we often call physics inform. In our context, power system inform machine learning. So now, we also might have recall that quite a lot of 20th century applied math, and I'm applied math professor, right, is kind of in between. So we use it almost automatically, but not quite. And sensitivity analysis is probably a most kind of representative example of that. So now, a little bit closer to home, to power system, we saw quite a lot of use already of machine learning, and not necessarily deep learning. So there are actually a lot of other areas which are maybe less hot today, but still important component of machine learning, in particular graphical models. And we usually use it for, faster, more efficient computation, basically speeding up. And that's what I'll be talking about today. We, of course, also think about completing what we don't see, so incomplete data. We should always rely on ground truth, so that's basic thing in machine learning. You need to have data. This data is not necessarily coming from measurements, it may be coming from simulations, and that's actually will be my story today too. And then, in terms of the System 1, System 2, what System 1 today may become System 2 in the future. So it's actually very, or other way around. It's actually kind of fluctuates. So we'll see it on examples too. And Right, so let me now kind of very briefly mention kind of subjective and my own prehistory in this topic, in the topic of using machine learning in power system. So we've been, well, it's not only my work, but mainly work groups I was involved. So we did it for structure learning, and that was kind of graphical model based. We've been learning ODE in this case in the context of power system community and swing equations. Well, color coding at this slide is actually about, so green would be physics informed, so coming more from power system side and then putting a little bit of machine learning, as opposed to red, which is completely forgetting kind of power system logic and black box type of things. But there is also yellow, when you kind of mix things and you put a hierarchy of models. And that's, I would argue, is actually probably most sophisticated, most important thing we need to do. I'll not be there today in my talk, but for some topics like creating models of generators, I thought succeeded. Well, and that's couple, well, some number of other topics, putting it just as a reference, and if any of you will want to discuss it, I'm here. But now, turning to actually what is the topic of my talk today. So we'll be discussing the specific question of economics, of power system economics, and specifically this question of edification of allocational marginal prices and economic dispatch. So people behind this story are Laurent, Robert, Yuri. I was expecting Robert to give a talk. Unfortunately, he got COVID. He already recovered, but he was not able to come. So now the setting. And here I'm oversimplify a little bit. So it's not a complete setting which we are dealing with. And I'll put a little bit more general setting later on. But that's just to start. So we have this kind of simplest possible formulation of power dispatch, OPF, what we call. Quadratic cost, well, I miss kind of type, so it's not linear programming, it's quadratic, but convex programming. And we have power flow in the conditions, and we have line constraints. Let me ignore generator constraints, and there are quite a number of simplifications, right? So it's the simplest possible formulation. So now, important observation, and that's actually very typical and in practical settings, actually in all of our experiments with OPF, very few lines are saturated in an optimal solution. Right? So those inequalities become active in a very, they may change those lines, but there are very few. Sparsity is behind. And now a challenge, right? We have a configuration of loads, or more generally loads and renewables, so basically not controlled degrees of freedom. They change all the time. And we want to run this, well, economic dispatch for many configurations. And even though this quadratic programming is quite, fast, efficient, we want to make it even faster. So that's what we will try to do. Do it faster, and yeah, so basically even faster than you can do normal quadratic programming. So that's basically a setting. That's my task. So now, projecting it back to the system 1, system 2 consideration, I'll basically be using this important information. Well, important information, there is a lot of physics in here, right? So that's my starting point. So that remains system 2. But it will be something which I'll outsource to system 1, and you'll see what is that. But before doing that, so a little reshuffling, which is nothing fancy, I basically go to this, what we call PTDF, power transfer distribution factor formulation. I get rid of phases, and I only have basically generator degrees of freedom stay, and this phi is known to me. And yeah, so what I'll be discussing, of course, is generalizable, so you can use it for a COPF, of course, under current conditional linearization. So that's a setting which I'm kind of thinking about. So now one more kind of formal mathematical step. Of course, it's very natural to go to Lagrangian, right? So you put your constraints, which are, well, power flow equations, but most important, well, power flow equations I already got rid of, PTDF, but I still have this line constraints. And line constraints, I'll put them with Lagrangian multipliers. And, well, here it's also passed to LMPs, right? So we know that optimal solution will also produce me this, well, dual variables, which are LMPs. So locational marginal process. So that's the beauty of this quadratic programming formulation. OK, so now KKT conditions, which is basically what I'll be massaging, and that's where I'll be putting the system one thinking into. They also have very good meaning, so kind of system two meaning, if you wish, financial coherency condition. So in particular, revenue adequacy. So if you basically sum all of those LMP-weighted contributions on the generation side, it will be well, less than what you have on the load side. You have enough funds on the kind of collected by system operator. You also you have cost recovery, and overall you basically like that, and you want to kind of reduce model, and that's what I'll be discussing. So that's kind of on engineering desiderata side. Okay, so now system two ideas, and that will be linked to this. Well, to strong duality, to my KKT condition. So what it basically means, it means that the part of Lagrangian is associated with inequalities, or the optimality should be equal to 0. But now recall that I was attracting your attention in the beginning of this presentation to the fact that there are very few lines which are saturated. Suppose I know which lines are saturated. Let me assume that I know. Then, of course, you immediately see, well, remarkable reduction of complexity. Well, quadratic convex programming, you might say it's easy, but solving linear system of equations is way much easier, right? So it's a kind of computationally sort of magnitudes or orders of magnitude easier. That's what you'll get if you know which lines are saturated. And that basically gives you idea of, so this kind of, linear algebra side remains my system 2. And now system 1, which I'll delegate to machine learning, will be edification of those saturated lines. And so that's basically what we'll be doing. That's now let's see how it works. So for that, I need to have machine learning and nothing fancy. So actually, that was exactly the point. We didn't want to have anything fancy, and we choose the simplest possible neural network. You can imagine which basically was enough for us. So CNN for layers. What did it do? So you have input. And input are configuration of loads, or resources which contribute this problem. And then output are those saturated lines. So 0, 1 outputs. And well, there are some technicality how we implemented it. As usual in kind of this machine learning neural network business, you need to define loss functions. So that's more or less done through this logistic regression. Again, nothing fancy. So, and that was not a point, I mean, to make it fancy. Yeah, so now let's see how it works. Okay, so importantly, we didn't want yet, at least in this project, to extrapolate. We're just in the business of interpolation. So interpolation means that for given configuration of a unit commitment, and unit commitment means generators which are well, fixed, so there are generators which are available. So we consider different configuration, and training was specific for this particular configuration. Well, I give here 3 examples of configuration, and those are lines, I'm sorry, not lines, generators which are free, which are basically contribute this generation dispatch problem. So now, and thinking is that this is operational. That's what you'll operational, but thinking or trying to predict what will happen when there is this window between two unit commitments. And now we generate a lot of samples for each of this configuration, and we basically train on those samples. Well, number of samples is, of course, parameter we need to follow. We also want to play with level of a noise. The level of a noise may be associated with probably more with renewables than with loads, those degrees of freedom which will be changing within this hour between two unit commitments. Okay, so now what you see that, again, so first results for different level of noise, and that's that's a little bit of noise, and by noise I mean a level of noise. So for each of those training sessions, it was different level of many configurations. And all right, so we need to access a quality of training, first of all, and of course this quality of training depends on a level of noise and depends on the configuration. So we, kind of common sense tests, it should decay with a noise, so that's what you see in this table. Then, of course, we don't want to overfit. So that's a standard thing which you do in anything machine learning. So you train on samples, on one sample, and then you test it on other samples. That's kind of checking that we are not overfitting and that we are good on that side. Remember I was mentioning other criteria like adequacy criteria, right? They were not explicitly in my loss function, so I post factum can check, and that's of course system 2 type of checking, so power system kind of informed testing, and that's what we've been doing too. And interestingly enough, when you test those different configurations, and again, configuration of generators available for training. And yeah, so here what I'm showing you is on IEEE 118. I'll tell you a little bit more and more realistic system, bigger system. You will observe that your scheme, the scheme, performs very differently on different configurations. And here you see dependence on basically level of performance, quality of performance. So if it is very small number, that's good. If it is spike up, it's not that good, depending on fraction of sample, but basically a number of samples. And what you see that in what is good for one configuration in terms of number of samples is actually not as good for another. So if you have fewer samples, then you run into troubles. And troubles are quite interesting. So they are phase transition types. You basically go from a perfect and very good reconstruction to basically failure, complete failure, which is also quite instructive to know that, to see this behavior. So sharp changes. And so larger systems. It's not in the paper. It's what we hope to report soon, but preliminary results. And that's, by the way, this model which we are using here is much more realistic. It's developed by within this RPE project, which Dan Bienstock is leading. So here are details. So we more or less tested the scheme on that, and those are preliminary results. More to come. Also, again, it's an opportunity for me to emphasize. We start with very simple neural network. If we are not getting satisfactory results, we are basically in this regime when we are on the wrong side of this phase transition. So basically, nothing works. We probably need better machine learning, or our hypothesis of what hypothesis about strong correlations between configuration of noise and those saturated lines that we can basically have it expressed in this one function. It may be wrong, then we basically need to reconsider. So that's, in this regards, empirical test. So take-home message for what I was telling you today. We had this very simple problem. in the future will be more sophisticated problem, quadratic programming in this case. We split it in two. We split it in an even simpler problem, which is linear algebra problem, and, well, this very simple classification problem. And the split was system 2 and system 1, and we suggest that this approach is quite general in a methodological sense. So it probably will be applied to many other problems, not only in power system, but power system in particular. And the challenge is, well, system 2 challenge, power engineering challenge is to identify weak points and see what, hopefully not very complicated part, which you outsource to deep learning. And if I have, do I have a minute or two or not? Yeah, you need to close. I need to close, okay. Maybe I'll not go into details on that, so a couple of slides. That's along the lines of what Spiros and his team were discussing, so I certainly very much believe about, that we need to work on developing trust in AI, and so some ideas about that in here, and so kind of desiderata, well, I consider myself serious, and that's kind of what I'm planning to do more or less, in particular in a power system context. And that's shameless advertisement of my program. So I'm chair of this applied math program. If you have, it's PhD program, University of Arizona, Tucson, and we are quite unique. We are doing applied math broadly defined, in particular in application power system. If you have any good students who may be interested in going to Tucson, let me know, or give them my contacts. Thank you.
So thank you very much. We got time just for one question before opening the panel.
Yes,
please.
Patrick Nonciatici from RT. Thank you, Misha, for the very interesting talk. But my feeling is that we have to solve the real problem, So this problem, we're solving it for, 2 decades. I can show you some papers on the 70s. So the problem is more the topology, for example. So then if you are not sampling the topology, the substation configuration, I want to push machine learning because of that, not to solve the classical problem. The classical problem is so easy. So we are solving that all the day, every time, and with this active set, with some a priori knowledge from experts, not from machine learning, but of course we can put machine learning for that. The problem is more to solve the real problem, for example, with the topology, and then you need to change completely all the framework and to go to this graphic neural network or things like that.
Well, there are many problems, and I do believe that one step at a time. Well, here it was motivated by...
There is no continuity. There is this phase transition that is not possible to have a continuous method that is able to... You have to change completely the method. So it's not...
Well, I'm not suggesting, okay, this phase transition is a feature of my approach. It's not a feature of reality. So if you'll be doing quadratic programming, you'll not have it. So it's a handicap of a method which I use. But method has advantage. It's speeding up. So now, what you're telling me, we have... Can I try to answer?
Yes.
Not in a power system. There are linear system of equations. Yes. And we have a lot of beautiful approaches, yes, which instead of n squared reduces to n log n, yes, and will be more. It's simple. It's much simpler than real problems, but we still pay attention. So that's you should view what I suggested here. And another kind of it's RPE is project which basically we wanted one step at a time, and we'll be talking about unit commitment, which is in our particular project, we are not considering reconfiguration. Some other, I think, Shmuel team, right? So Shmuel is here somewhere, or was. Yeah. So there are many problems, and
of course, but you need to clarify this problem because for me there is no continuity between this kind of very easy problem to solve and the real one. So we need to have a new. But
yeah,
I like easy.
Discuss during the. Can you Can I invite all the speakers to sit here at the table? Thank you, because I think there are several topics that should be addressed. So let me invite. Okay. So let me open the discussion. So please, if you have got some questions. Yeah, please.
So Jochen Stiassen from DTU. So actually connecting to what Misha said about the system 2, bringing in the physical knowledge. So the curse of dimensionality, I think, affects basically all your approaches in the end. And I wonder how you think about bringing in physical knowledge and more system 2 ideas to address that, because sampling in high-dimensional spaces will fail eventually. So yeah, it's an open question for whoever wants.
I can start. No, it's exactly perfect point you're making. Right, so course of dimensionality in this case is, well, in my story which I presented, is in the number of samples you need to have, and for each sample there is a certain complexity. So you basically reduce it. In this case, you identify a weak point, right? And you gain on that. So what Patrick wanted me to address, probably over there will be sparsity of those lines which you need to switch on or switch off. Most probably will be very few at each configuration. That's system 2 thinking, right? I mean, or information which we are getting for practice. And then once you delegate it to well, what you identify as a kind of weak point, which allows you to reduce, well, dimensionality. We've already fight course of dimensionality, yeah. So you have a combination of the two. So that's my answer to that.
Yeah, Maria, please.
Maria Ilic, MIT. So I think that if one takes Mojde's flowchart, she emulates what's happening on the system and tries to relate Misha to your piece, which solves one part. I think the question that maybe Patrick was asking was, how do you, as things are evolving on the system, it's almost like emulating cascading failures, and what do you do? It's much deeper problem than just solving quadratic programming, right? So I guess the question is, how do we do that? Do you start from some simpler process that Mojde defines, and then look at every step and say, what can AI do to simplify that step, and this step, and that step, and then you link them? That is, I think, maybe how we can connect, because the system operators can use faster computation for a particular thing, but what they are really after, they're after advising for what Mojde was showing in her diagram. Things are happening, and I have to tell them what to do as things are happening. So you think, for both of you, but for you, Misha, do you think it's realistic to get there with AI? That is your real system too. That's the physics.
Well, I agree that identifying those weak points is difficult, and the more complicated problem, the more complicated it is. But that's why we like to talk to system operators, right? We all like to talk to experts who are, well, there are always some current solutions, right? And through current solutions, we know sometimes don't, what are weak points in those current solutions, and focus on those, identifying. And once we focus and simplify them. So my point is that, I guess, using deep learning, I also guilty in doing that. But very often it's too powerful and you don't really need it. And it's kind of masked this, well, power system side. And maybe we don't need to do it all the time.
Okay.
I can add to that. I think that, Maria, you framed it really well. And I think that all of these different phases, like the first phase of improving the system resiliency is the ability to forecast what is coming, and AI is a great tool. And with the amount of data that we are available from PMU and micro PMU, it can really help in terms of prediction of the events, not only the initial event, but also how the event is going to unfold, at least a warning ahead of time. So I think, yeah, you framed it very well, and that's how I see it as well.
Okay, thank you. Please.
Okay. Yeah, I'm Kumar Vanagamurthy from Clemson University. So my question is to all of you. So AI, machine learning, deep learning, right? So artificial intelligence is great when you can have the right problem to solve. You have to justify why you need AI. But the other thing with AI is also, like deep learning, is that you need a lot of data to train this kind of models to learn power system dynamics. And of course, power system, depending on what kind of problem you're solving in power system, it can be a nightmare. Okay, so deep learning and power systems, personally, I don't think it's a way forward because of the amount of data you need with deep learning, right? And it's very brittle. Once you develop a deep learning neural network, it's very brittle, which means that when power system dynamics changes, that deep neural network is not valid anymore, okay? So we have to look at, but AI is great. Don't get me wrong, AI is wonderful in solving problems that otherwise other methods cannot solve, especially when we now look at a lot of data-driven methods, okay? So my question to you is, how do you see, power system is an evolving system, dynamic system. The dynamics are changing. So how do you see AI moving forward in being really utilized for solving problems other methods cannot be solved? So it's a general question to all of you. Thank you.
I work mostly with deep neural networks in my research, at least, and I can agree with you that it's very time-consuming, especially when you work with dynamic systems to generate that amount of data. Typically, most just work with time domain simulations, and generating that for quite a long time takes a lot of time. Then I think we should also remember computers are getting faster. We've heard people talking about quantum computers, etc. So I think theoretically in the future, generating data might be less of a challenge than it is now. I think other challenges, such as getting a representative training set that covers all the states, might be less than just the computational challenge of doing so. But I agree with you, it is brittle, and if you don't have a good data set that covers it, you will not get accurate predictions, for instance. But we've seen other presenters also talking about verification. You can verify what kind of regions it's actually accurate, and maybe you don't have to use neural networks for all the kind of applications. You can use it as, if it's working in one kind of region in the state space, use it for that. And then, I don't think any system operator would take the conventional systems, remove them, and just put a deep neural network controller, for instance, or classifier. I think they would continue having their old systems as well, and maybe having this one on top of this. That's what I would guess.
Yeah, I'd like to express also my point of view about this. Is an interesting point. I think that to solve a problem, the first approach that should be applied is the conventional one. If the conventional solution approach works well, I don't see why apply artificial intelligence. In my own opinion, artificial intelligence could be a crucial rule in allowing the control paradigms in power system to evolve from event-based to model-based. If you have to analyze data streaming coming in real time and you have to take action in real time, I think conventional methods could be not able to do that. There is another keywords that I'd like to ask you, what do you think, is digital twinning, the digital twin of a power system, which is mainly an emerging tool in power system operation. And system operators are very interested in understanding how this tool could be useful in supporting power system operation. I don't know what you think about that.
I agree with what you're saying. I think that, yeah, as you mentioned, when a conventional approach that can model the physics of system can perform well, then that's probably the safest approach. The problem with a lot of ML-based approaches is the black box nature of it, of course, and but there are, of course, approaches that are also presented, like causal learning and other approaches. Experts probably can talk about it more, that enables better understanding what we are getting out of the black box. So that's also another factor for that type of problem.
Yeah, please. Oh, sorry, Micho. Please go ahead.
Yeah, couple of comments in terms of, first of all, how many samples. Well, that's a number of, well, that's degree of freedom, which you need to consider. And not often you cannot afford to have a lot of data, a lot of samples. Often you just, yeah, it's a waste. And that's a part of consideration. So I completely agree that whenever there is a classic method, you should use it. But it's also, I want to reemphasize that it's good to have a spectrum of methods, and going all the way from physics-based to power system-based and no AI whatsoever, and then extreme of black box of different types, and many things in between. And basically for your current regime, how many samples you can afford, what is accuracy, and other characteristics. Well, I was showing this phase transition, and it's oversimplified. Well, two-dimensional space, it's high dimension. That's a part of the game. And then for some problems, we don't need it. For others, we do need it.
Okay.
Reza Shafiqa from University of Vasa, Finland. Thank you for all the presentation and the discussion. One of the main concerns of the utilities for using AI-based methods on solving the problems is the repeatability of the methods. I mean that, for example, if we give one set of data, exact set of data to the neural networks in each iteration, or even after training, full training, it will give us different results. For example, now I give the system the data and give some results, for example, location on marginal price and the auction winners and so on. And the same data with the same system give me different results. And it cannot be used in the market, it's different. Sometimes we can use it for many applications, but when we are talking about the money, financial things, and so on, it can be very risky for the system. Which utilities can accept it, that we have different results, just with exactly the same data? How to close the loop? I mean, how we can set this as a statistic, it can be performed well for the system, so any utility can accept it.
Okay, so you mean that when you train a model with exact same kind of data, it would provide different results? But then I guess, from my point of view, then you probably use too less data to train it completely, and possibly haven't trained it sufficiently. Because I mean, obviously, if the data set is very small, you can get big variance in how you train it. But I think it should really achieve, I mean, very close. I mean, possibly not the exact same answer, but very close to it, at least. That's my experience. If you have large enough data sets that you train it on.
Well, my understanding is that you are from utility, or you represent utility. And the type of information you provide is extremely system 2 information. So if you'll say that different type of data gives you different results, for classic method or whatever AI method, that's very important input information. That's part of the reason we considered, we originally wanted to have a more complex system, as Patrick wanted me to study. Well, combination of everything. But then we realized that, well, either we need to have too much of a data and we are getting God knows what. And that's why we focus on fixing unit commitment going to a PF. So that's input which you are getting from experienced people. So now in machine learning, of course, we have this interpolation versus extrapolation. Extrapolation is much more demanding, much more difficult. You're going to another regimes. to do it, you need to have more data, you need to have more sophistication. If you believe that that's a bottleneck, you really want to have one method and not retrain, so be it. Then it's more challenging and more AI should be put in. But on the other hand, do you really need it? If you, for this hour, you know that you are more or less within these conditions. So it is an interactive process.
I see. Thank you.
So, yeah, Spiros, with you. Thanks. It's more a few comments, but
yeah. May you introduce?
Yes, Spiros from the.
Oh, sorry. Yeah, I didn't catch it.
Yeah, I was too fast. So the first is, I mean, AI is indeed a black box, and actually our efforts should be to address this. If we are to apply a black box on power systems, so there should be for problems that were not, it's impossible to solve otherwise. So also for what Misha presented, I think also this is where Patrick's comments going. So for example, we can have optimization problems, and we have actually also done that, that are intractable. So MILPs, that are very large MILPs. And that's where learning the active constraints or learning the active set can actually help us identify a solution at least. What Miadreza said, we can have verification. That's what also neural network verification, trying to get some certificates about how neural networks work. And this can also help gain this trust. Because indeed, every time we are going to have, you might have different results because it's a very non-linear optimization problem. But knowing how it behaves and where it does not violate whatever constraints you have, that's important. So these are just some thoughts about trustworthiness, repeatability, and where we can apply neural networks. I have one more comment related to Bringyar's presentation that I'm actually a co-author. And the question that Dominic raised about the noise. The noise in the real quantum computers is actually a bug. And that's what, so all these quantum scientists are trying to remove. But the strength of a quantum computer is the fact that the quantum has a certain probability of being 0 or 1. So we can model all these kind of scenarios by naturally through the probability distribution of the quantum. So the noise is a bug, but the quantum has some probability that we can take advantage of. That's the...
Yep, please.
Okay, Hamid Zaripur, University of Calgary. I just want to make a comment and pose an open, question to just not the panel, everyone. I guess, when it comes to AI, most of the enhancements and progress that we've seen over the past 10 years has been mostly in the area of speech recognition and video and pictures and those things.
Imagine process.
Yeah. So, and it's a very important thing there. And making a mistake in a speech recognition or tagging your friend on your Facebook, making a mistake is acceptable. Like 96% accuracy in a lot of areas that AI is being used these days is amazing. So that 4% is always ignored. I guess in a lot of power systems and energy system problems that we deal with, nobody is interested in the 99.9% of events. That 0.1% of events are important, and the cost of false positive or false negative could be hugely different. So I think moving forward, we always need to be mindful of this huge imbalance in the cost of making a mistake in our domain versus other domains. I mean, we can learn a lot from the health sciences because there also misclassifying a patient is very, very costly. So, for the patient, yes. Yeah, exactly. But, I mean, to be fair to the healthcare, I mean, they don't want that either. So I'm just posing this comment and probably a question that how we can make sure that we are not missing out on that 0.1% or even less events that are actually important and not being occupied and misled by the 99.999 accuracy that we might get on unimportant things. Thank you.
Yeah, let me just give a brief reply from my point of view. The answer is reliable computing. Is, in my own opinion, another enable methodology that could be useful in power system analysis. It means that it's a paradigm for computing which allows you to consider all the possible instances of the uncertainty. In my own opinion, could be play an important role. Also, in estimating the very worst case instance of all the uncertainty affecting power system operation. But it's only my point of view. Obviously, I do like to ask if you have got some opinion.
Yeah, I just can comment also because my applications is directed towards safety critical application with mitigating long-term fault stability. So I completely agree with you that a system operator won't care if my algorithm can mitigate instability in 99.9% of the cases. They would care about the possible time that it won't work. So I fully agree with you, and I think I haven't myself researched on it, but I'm guessing, and I think I've seen other papers that does work on it, and I'm not sure automated driving as well, that's a big area as well, but you cannot have too much misclassifications. That will also have a major impact. I believe at least that the research is going forward very much in this area.
Okay, we have just time for last comment. Just the last one, because...
Indeed, in a classic, now classic deep learning, there is much less attention paid to outliers, and they usually just cut. So you prepare data, and cutting this, less than 1% or whatever. But it doesn't mean that people don't understand its importance. There are different applications. Power system is not unique in terms of, importance of those rare situations. And there is something to learn from deep learning, but also that's an outstanding question, of course. So we want to work out new methods and new techniques for events, or events which we never saw.
Okay, thank you very much. So let me thank again all the speakers and all of you for attending this panel.